Hey guys, and welcome to another reteach video. This one's for Unit 6. Remember, at the end of the video, you'll get the password to retake or make up the Unit 6 test. This test proved to be fairly difficult for people, and so I have several questions here to go over. These were the most difficult ones on the test, and so hopefully this will help you on the retake, or if you're making it up, the first time that you take the test. The hardest question on the test is right here. Which of the following parts of a dry cell corresponds to the salt bridge shown in the diagram? And then you're given this diagram right here. So the first thing you have to know is what the salt bridge is, and hopefully you know this is the salt bridge right here with the Na and SO4. And now it's asking you what part of the dry cell it has the same function as the salt bridge in this diagram. And so you can look at a diagram of a dry cell, and here's one right here. We have a diagram of a dry cell. Let's make sure we can see it all. And the diagram of the dry cell, you can see the small layers here right inside the battery wall. And your choices are, most people either picked solid zinc layer, or the cardboard separator. The solid zinc layer was by far the most common, and that is not the answer. It is the cardboard separator. Oops, it's a bad job circling, but the cardboard separator is the answer. That's the same thing as a salt bridge in a dry cell. It's kind of separating the two halves of the reaction, right? Just like the salt bridge kind of connects or separates the two halves of the reaction here, the cardboard separator is in between the paste and the zinc. It's kind of separating those two half reactions. Alright, moving on. If molten sodium chloride is split by electrolysis, which of the following reactions occurs at the cathode? Now, there's a couple of them on here that are similar to this, that they sound tricky because you might be like, well, what is molten sodium chloride split by electrolysis? What does that even mean? However, you don't even actually have to know what that means. What you do have to know is it says the following reactions happens at the cathode. And now hopefully we know now that oxidation occurs at the anode and reduction occurs at the cathode. And so if I know that reduction occurs at the cathode, I can look at my answer choices and just pick out the ones that are reduction reactions. And once you remember that reduction occurs at the cathode and oxidation occurs at the anode, then it becomes a simple matter of, finding the reduction reaction in our answer choices. And when I copied these over, unfortunately, the arrows didn't copy, and so I drew them in here. So the arrow goes here in between the electrons and the Na, and the arrow goes here and here and here. And we know a reduction reaction is when we're losing, or when an atom is gaining electrons, right? Reduction is when we're gaining electrons, and the only one that's gaining electrons is this top one. And so if it's occurring at the cathode, it must be a reduction reaction, and then this is the only reduction reaction in the answer choices, and so it must be that one right there. 2 Na, liquid plus 2 electrons, and then here's the arrow, react to form, 2 Na, and then the charges unfortunately didn't transfer either. Oh, they did actually, yes, so we went from plus, so we were at 1 plus, we added 2 electrons, we have 2 Na atoms, and so now we're in neutral, we're at a 0 charge, and so we were reduced. We were at +1, now we're at 0 charge, and so that's the reduction reaction. Next, here's the overall reaction of a mercury oxide dry cell, and then here's the reaction. In this reaction, which of the following gets oxidized? So this is another kind of tricky question, in the fact that you've never heard of a mercury oxide dry cell, or you maybe have never seen this chemical equation before, and this should actually be the react to form arrow goes right there. However, it's asking you which of the following gets oxidized, and we know what oxidation and reduction is. And so if we look at our equation up here, we can see that zinc starts off by itself, just Zn, and then it ends up being bonded to an oxygen. And that's another definition of being oxidized, is when an atom or an element forms bonds with oxygen. And so which of these elements got oxidized? Well, zinc got oxidized, right? It started out, was not bonded to an oxygen atom, and at the end in the products, it is bonded to an oxygen atom. All right, going up here. So of the metals, and then we get 4 metals, Au, Fe, Na, and Cd, which will not give up its electrons to silver in a redox reaction. And then you get this table. And remember, this table means the most active elements, the elements that are most likely to give up an electron, are at the top. And then the least active elements, the ones that really want to hold on to their electrons and do not want to give them up, are at the bottom. And so first thing we need to do is find silver, Ag. And so here is silver. It is not very active. And so then we want to know which will not give up its electrons to silver. So which one, essentially, which of these 4 want to hold on to their electrons more than silver does? And so let's find these 4 on our chart. So Au is right here, Fe is here, Na, and Cd. Okay, so now, yep, we have silver. So which one wants to hold on to its electrons more than silver does? Which will not give its electrons to silver because it's holding on to them too tightly? And then after we know that, I think clearly the answer is gold, right? That wants to hold on to its electrons a lot. It does not want to give them up, so it will not give them up to silver. These other 3, these will all give their electrons to silver, right? Because silver wants them way more than they do. Silver wants electrons way more than Cd, cadmium, Fe, iron, or Na, sodium. And so the answer is gold, Au, will not give up its electrons. All right. And I have one more, well, I have 2 more questions to go over, actually. A different sheet. So which of the following statements is true about a nickel-cadmium dry cell? So here's another one of those where it's talking about cathode reactions or anode reactions, and we have to know what happens at a cathode and an anode. So you don't have to know anything about a nickel-cadmium dry cell to get this correct. You do need to know what happens at the cathode and what happens at the anode. And as, again, hopefully we all know, oxidation happens at the anode and reduction happens at the cathode. Okay, and I paused it for just a second so I could draw in the reaction arrows here, because again, they didn't copy. So we're just going to go through these answer choices and see which one is true based on our knowledge of cathodes, anodes, oxidation, reduction. So the first one, the cathode reaction is this, and so this should be cathode, so we need to know this should be a reduction. Should be a reduction. It's happening at the cathode, so this should be a reduction reaction. And if it's reduction, remember, the electrons will be on the reactant side, because reduction means you're reducing charges, you're gaining electrons. And if we look here, oh, nope, the electrons are on the product side, so it's actually losing. Cadmium is actually losing electrons, so it's actually being oxidized. So this is not correct. This is not true. How about this one? The cathode, again cathode, so it should be a reduction reaction, is this. And okay, so I look and I say, oh, okay, so there's electrons on the reactant side. Okay, so this is a possibility, right? So I'll make a little mark here, but we need to check the rest of them still too. This is a possibility because it's gaining electrons, so it's being reduced in charge. Okay, next one, the cathode reaction. So again, cathode should be reduction, is this. Okay. And I can see, again, I don't even see any electrons in this equation. Right, so that's probably not going to be the answer. I don't even see any electrons moving around. So probably not the third one, C. And then I'll check the last one, the anode reaction. So this should be an oxidation reaction because it's at the anode. And I see here the electrons are on the reactant side. And so I know that's not correct because if they're on the reactant side, then something is getting reduced in charge, and it would be a reduction reaction. So it's not this. So B, the second one, this is indeed the answer, because the cathode reaction is this. It's the only one that has electrons on the reactant side. All right, last one. During the electrolysis of brine, where does the hydrogen in the hydrogen gas come from? Now, this was something that you just learned in your lessons. However, if you don't remember this, you can still figure it out by kind of thinking about the elements here. So what I know is that it's asking, where does the hydrogen come from in the hydrogen gas? And so I look here, so I'm thinking, where could the hydrogen come from? Well, chlorine doesn't, it's not hydrogen, right? So it can't come from chlorine. Sodium is not hydrogen, so it can't come from there. Water, hopefully we all know water's H2O. Okay, yeah, it definitely could come from there. There's hydrogen in there. And then the battery, it's probably not coming from the battery. That's, it's a battery. We're probably not getting hydrogen gas from the battery. So if you're down to those two choices, water is actually the only thing that has hydrogen in it that could be released as hydrogen gas, and so the answer is indeed water. And brine, so like I said, this would be something you'd have to remember from your lessons. Brine is salt water, basically. So that's why I was asking you for sodium chloride, because it would be like putting NaCl in water, having a solution of salt water. Alright guys, I hope that helped. Remember to write down the password coming up, and good luck on the test.